Give it out.
Yeah. Thank you. Yeah. Actually, I can show you my iPad. I spray everything. Oh. I feel like. Yeah. I can show you.
Yeah, it's not. It's really.
We have a lot of alumni.
Oh, really?
Yeah.
The kid dance?
Yeah. The kid over there.
What do you mean? I like it. Oh, no, I
live like. Final graduated. Yeah, I got one.
I've always tried to last time for the past two. I've always tried to talk.
I met him a year ago, and when I first came over, they made me take a CAD class. Oh, that's one of two.
What do you go for? What do you do? What do you have to do? When you do revision,
Maybe, but yeah, well, I didn't go. I just some days and things are all good.
Oh, really? I like that one. I think I told you, you can always do metrics.
Once I practiced like someone that weighs like 50 pounds. Your sister. I don't know, it's very common.
I was thinking buying one. I was out at my knee shop because I went to pick up my knee guards. And I found the helmet on sale. I can get another year and a half, 2 years of it. Because it was made in February 2019. It's on sale for like $320 before tax, but it's got an additional like 20% off. So if it comes out to like $300 at the door, I'll take it. Then I'll have 2 helmets.
All right, it's 5:30. Let's go and get started using. All right, good evening, everyone. How's everyone doing today? Hungry. Yeah, I'm hungry. I'm hungry too. I'm always really hungry. But you need after this one. Okay. So the plan for today is we're going to just continue on with our lecture notes. So we're just kind of trudging along. So we're taking a break right now. It's just mostly just to give you guys a chance to work on the projects. So the activity 4 was due last night, and so now I'm not going to sign anything else until the project is due. So you guys are free to focus on that for the next 2 weeks. So if you have questions on the project, definitely feel free to ask. My office hours are going to be over to the next ones. All right, any questions I can answer before we get started for today?
Question again.
Yeah.
Are you not supposed to be able to run the mesh on the solid model from yesterday's time?
Sometimes you can't. So so about like 20-25% of people can, but if you get an error, that's an expected result too. Yeah. So if you get an error on that, then yeah, totally.
I was able to mesh this from solid.
No, because I had the same question because at least the mesh conversions, I couldn't achieve that.
Oh yeah, if you're not getting mesh convergence too, were you doing something like the stress?
No.
Okay, it should convert for the deformation. Maybe we can take a look. But the stress sometimes can be hard to converge just because of the limitations of the software. Right. But the deformation should convert. But we can take a look. All right, any other questions on activity 4 or anything?
You said the midterm is before Thanksgiving,
Yes, so we're gonna have a midterm exam before Thanksgiving.
so it'll be second weeks of the.
Yes. Yeah, whichever the last lecture before Thanksgiving. So like the second or probably second weekend.
Thank you.
Yeah, the date should be on the syllabus, so it's just whatever date. All right, any other questions before we start for today? Okay, all right, so let's go ahead and get started. To get started today, actually, I'm going to go ahead and scroll up just a little bit, just so that you can kind of see kind of where we left off last time. Okay. So last lecture on Tuesday, we introduced this idea of a different element type, or not really different element type, but different. I guess it's we introduced this idea of truss elements into the direct stiffness. But up to this point, we've only been working with springs. So springs are, one way that you can do the direct stiffness method. Trusses are another. Okay. And before we finished up on Tuesday, we kind of started talking about this idea of doing these problems in 2 dimensions. Okay. Because going up from 1 dimension to 2 dimensions is actually going to be quite a bit of work. So we want to make sure that we can kind of understand. And so, before we do that, we have to kind of understand a little bit about coordinate systems, okay? Because, I think, so the way we motivated it last time was that, these element stiffness matrices that we've been working with, not only for the spring, but for the truss element as well, that's kind of, that was kind of derived under the assumption that, our x-axis is perfectly parallel to the long axis of the truss or spring, that whatever, okay? In other words, the tension or compression that we observe is going to be perfectly aligned with the x-axis. That's not necessarily going to be the case in 2 dimensions, because we may have truss elements or springs that are rotated, relative to that x-axis. Okay? And so we introduced this idea of having 2 different coordinate systems to kind of describe the same things. Okay. And so on the left here, what I have is what I call kind of a stationary coordinate system. And so the stationary coordinate system is one that doesn't move, and so it basically acts as our reference, throughout the entire process. And then relative to that, we may have something called a local coordinate system, which is a coordinate system that's arranged kind of or rotated to match whatever truss or spring element that we're with. Okay. And so, when I think when people talk about kind of frames of reference and coordinate systems, it can definitely be a little bit intimidating, just because the math involved in this can get tough. But I kind of want to emphasize the fact that when we're looking at different coordinate systems, it's really just kind of different descriptions of the same thing. Okay. And so to kind of illustrate that, I've drawn this vector in blue here, and so that vector in blue is exactly the same between the 2 coordinate systems. It's just the way that we describe it is slightly different. Okay, it's like an object in the real world, right? So you can't, maybe not all of you can see it, but there's a bucket of alcoholic wipes here on the table, right? So one way that I can describe that bucket is that it's roughly, I don't know, maybe like 3 feet away from me, right? Okay, but another way to describe it is that it's roughly, maybe 10 feet away from that. Right? The bucket is still in the same place. It's still the same bucket. It's just the way that you describe it is different, kind of relative to whatever your landmarks. And so you can think of coordinate systems as the same thing. It's kind of different descriptions of the same thing. And so let's start our discussion there. So, what we ended with last time was that if you have a vector, you can describe its components in two different ways. You can either describe its components relative to the stationary coordinate system, or you can describe its components relative to the local coordinate system. And so if we were to write this down mathematically, in vector form, it would look like this. So on one hand, we have the stationary coordinate system. On the other hand, we have the local coordinate. And so under the stationary coordinate system, if we use kind of the traditional IJ notation, it would look something like this, okay? So we have ux times I plus uy times j, okay? Where I and j here are unit normal vectors in the stationary x direction and the stationary y direction. So that's kind of, that's another way to kind of describe a vector. This is equal to the same vector, but described in the local coordinates. And so its components are going to be ux hat times I hat plus uy hat j hat. Or again, we have I hat and j hat. I hat and j hat are unit normal vectors or unit vectors in the local x and local y directions. And since these two describe the same vector, we can put an equal sign in the middle of this. So these two descriptions are mathematically equivalent to each other. Okay? Because it's the same vector. Okay. And so for the next, I would say maybe 20, 30 minutes, we're going to be working on this equation. Okay? And so we're going to kind of substitute some terms in this equation so that we can kind of draw a kind of a more direct relationship between these two systems. Okay? In particular, what we want to do, so in order to kind of properly relate these two, we want to come up with different expressions for the unit vectors and put them in terms of the others. So in other words, what we're going to do is we're going to replace I and j with expressions that involve I hat j. And so after doing that, we're going to be able to kind of relate these two together. In fact, we're going to be able to get a system of equations. Okay, so let's go ahead and start doing it. So actually, let me do this. Let me do this again. So let me draw the stationary coordinate system. So this is x and y. This is the stationary coordinates. Where the local coordinates is simply just going to be a rotation from the stationary. So we're going to assume that so in order to get the local coordinates, we take the stationary coordinate system and just rotate it counterclockwise by an amount of 8. Okay. Okay. Okay, so let's draw a picture of the I vector. So I vector, okay, is just a unit, of vector in the x direction. Okay. Right, so the I vector is just a vector with magnitude 1 that's in the positive x direction, stationary. Okay. In addition to this, let's also draw the components of this vector in the local system. So we're basically taking the unit normal in the x direction, and we're going to describe it using the local coordinates. Okay, so that's going to look something like this. So we know that the local coordinate system is kind of rotated upwards by an angle of theta. That's the direction of the local coordinate. So we kind of draw a line here. So let's draw with the same origin. Okay, so if we draw from the same origin, because we're assuming that our local coordinate system is not going to be translated, it's just going to be rotated. Okay, and so we have the same origin. We built that line, and then let's also draw a line that's kind of perpendicular to that. And so we're going to form kind of a right triangle here out of that. Where this top part of the triangle right here, we know that this is in the I hat direction. So let's call this a vector A hat. Okay. Its length is not going to be 1, but we'll be able to kind of describe it soon. Okay. And then this vector B hat. Okay. Since this vector B hat is perpendicular to the A hat vector, we know that this is going to be in the, well, in this case, it's going to be in the minus J hat. So let's compute the lengths of the A hat vector and the B hat vector. Okay. And so let's use trigonometry for this. Okay. And so if the hypotenuse of our triangle is I without the hat, okay, that means the length of A is going to be equal to the length of I multiplied by cosine theta. Because we know that cosine theta is the ratio of the adjacent edge divided by the hypotenuse. Okay. And so if we multiply both sides by the hypotenuse, we get A hat is equal to I times cosine theta. Okay. But we know that the magnitude of I is 1, because I is a unit vector, right? And so a unit vector by definition has a length 1. Okay. And so this tells us that the length of A hat is going to be cosine theta. We can do the same thing for B hat. So for B hat, we can find its length just purely from trigonometry. And so B hat is going to be I times the length of I times sine theta. And since we know that the length of I is 1, what we get from this is that the length of the B hat vector is sine. That's good. All right. So now let's take our I vector here and represent it using A hat and B hat. okay? Because if you look at the way that I drew these vectors, right, and so if you look at the way A hat and B hat are arranged, you know, I've kind of attached the tail of B hat to the end of A hat, right? And so what this means is by vector addition, if you add two vectors together, then visually what happens is that you kind of attach them kind of tail to head, okay? And then the location where the last arrow points, that's the result of the sum. Okay? And so what we have is A hat plus B hat is equal to I. Okay. Because if you add those two vectors, you end up in the same place as the I vector. And so let's replace the expressions for A hat and B hat. Okay, so instead of leaving them as generic vectors, let's put them in terms of I hat and J hat, which are the local kind of the local unit vectors. My mind does that sometimes. So you know, when I draw I kind of draw the curve going to the right, and so my mind will say that, but then my pen will. So sometimes it will do J then I. So it doesn't really matter. They're both okay. So the A hat vector we know is in the I hat direction. So this is going to be magnitude of A hat times I hat. Okay. And then we know the B hat vector is in the minus J hat direction. So it's going to be minus magnitude of B hat times J hat. Okay. Right hand side is still equal to I. We've solved for the magnitudes of the A hat and B hat vectors, so let's go ahead and plug that in. We have cosine theta I hat minus sine theta J hat equal to 2. And so I box that expression. Because what do we have in this expression, right? So what we have in this expression here is an explicit relationship between the unit vectors in both systems. Oh, question, yes.
How did you get AI minus BJ equals I?
So I basically, so for by vector addition, right, we know that A hat plus B hat is equal to I, right? And so if you follow kind of the path of the vectors from there. And so what I did from there was I said that, okay, I have this A hat vector. Let's put that in terms of the unit vectors I hat and J hat. Okay? Because the way we drew this triangle here, we know that the A hat vector was pointing in the I hat direction. So what we can say is that the A hat vector, one way that we can represent it is that we can take the magnitude of that vector and multiply it by the I hat vector. It's going in that direction. And so we kind of broken up that vector into its magnitude and its direction. And the reason we have negative for the B hat is because we know B hat points down, or points in kind of a negative J hat. So that's where that negative. All right, any other questions on this? Okay. All right, so that's one equation. So what we can do from here is we can take this equation and then scroll back up here, okay? And we can plug that in for here. Okay. So that's one piece of the puzzle. But the other piece of the puzzle here is going to be for J. So let's kind of go through the same exercise and do the same thing. So just like we did before, we're gonna draw the J vector. Okay. And so remember, J is the unit vector in the stationary Y direction, so that's gonna just kind of point vertically upwards. Okay. And then we're gonna break this up into components in the positive I hat direction and the positive J hat direction. And so the J hat direction, we start from the same origin, is gonna be this angle here is theta. And so again, we'll call this P hat. A little more. And then again, we're going to have an A hat vector that's going to be perpendicular to the B hat vector, okay? Where the A hat vector again points in the positive I hat direction. Okay. All right, so once again, we're going to use trigonometry. So let's go ahead and find the magnitudes of the A hat and B hat vector. So we have magnitude of the A hat vector, in this case, is going to be magnitude of J times sine theta. And the magnitude of the B hat vector is going to be magnitude of J cosine theta. Once again, we're going to remind the fact that the magnitude of the J vector is going to be 1 because it's a unit vector. Okay. And so we get magnitude of the A vector is going to be sine theta. And magnitude of the B vector is going to be this cosine. Okay. And so once again, we'll go ahead and form our vector addition expression. So we have B hat plus A hat is equal to J. Okay. We're going to replace these with their expressions here. So we have B hat is equal to magnitude of B hat times J hat plus magnitude of A hat times I hat. Is equal to J. We plug in for our magnitudes for B hat and A hat, and we get cosine theta and J hat plus sine theta I hat equal to J. All right, and so now that we have an expression for I, we have an expression for J, we can plug both of these into our original equation that we started with. Just as a reminder, let me go ahead and write it down again. So we have X times I plus UY J Q UX hat plus UY hat J hat. I'm going to plug in for I and J here because we just found expressions for these. Okay. And so if we do that, we get UX times cosine theta hat and sine theta J hat plus UY sine theta I hat plus cosine theta J hat. Okay. This all equal to UX hat I hat plus UY hat J hat. All right. So let's take this expression and then let's rearrange the left-hand side. So let's rearrange it so that we kind of group terms in terms of I hat and J hat. And so if we do that, we get the following expression. We get ux cosine theta plus uy sine theta hat plus minus ux sine theta plus uy cosine theta j hat equal to ux hat I hat plus uy hat j hat. We're starting off with a lot of algebra today. Well, we're only maybe about 20%. So there's gonna be a lot of algebra today. Okay, but let's do this. And so this part's easy. Okay, because if you notice here, we have an I hat term on the left hand side and an I hat term on the right hand side. Okay. And so what this is telling us is that these two terms that are circled in red, these two have to be equal to each other. Okay. And so we have ux cosine theta plus uy sine theta is equal to ux hat. Okay. That has to be true because both of those terms are multiplied by I hat. And then the same is true for the j hat term. So this term that I've circled in purple is equal to that term that I've circled in purple on the right. So we go minus ux sine theta plus uy plus theta is equal to uy hat. Okay. All right. And so we have a system of two equations here. Okay. And so what do we like to do when we have equations, systems of equations? We like to put them in matrix form. So let's go ahead and do that. And so putting this in matrix form, we get the following expressions. We have cosine theta, sine theta, minus sine theta, cosine theta. Okay. I'm going to extract out ux and uy, because those are the common terms on the left-hand side. And this is all equal to the vector ux hat and uy hat. All right. And so what we obtain from this is this matrix. Okay. And so this matrix is known as our transformation matrix. And the reason it has that name is that it allows us to transform vectors in one format or one coordinate system into vectors into a different coordinate system. In particular, look at how it's kind of used in this equation. Okay? And so if you look at this vector ux and uy, right? This is our original vector described in the original stationary coordinate system. But ux and uy are the components of that vector in that stationary system. Okay. What this expression here is telling us is that if we multiply that vector by our transformation matrix, then what we obtain at the end is that same vector, but described in the local coordinate system. And so kind of the engine that allowed this to happen, that basically kind of drives this this relationship, is that transformation matrix. Okay. And so of course, that transformation matrix is going to be kind of core to how we work with truss and spring elements in 2 dimensions. Okay. Any questions on how we got to this point here? Okay. All right. So this is good. So this is a good point right here, because now we actually have a way to relate these 2 things. Okay. So let's apply this. Let's apply this to our element stiffness matrix. So the process is exactly the same between a truss and a spring, but since we're on the subject of trusses, let's do it for a truss. Okay, so let's say that we have a truss element. We'll not make any assumptions on its direction. Okay, so we'll say that it's kind of angled maybe upwards. Okay, but we will assume that we know the direction, so we know that the element is angled upwards at an amount theta. Okay. And so if we were to describe the deformation of this truss element in its local system, okay, we would have the following results. So we have F1 hat in the x direction. Okay. We have D1 x hat. Okay. So that's the local force and the nodal deformation on the left node in the local coordinates. Okay. And then on the right node we have F2x hat and D2x hat. Okay. So same thing. So that describes kind of the local force and the local displacement on the right node in its coordinate system that's local to that element. So basically, all the trusses and springs that we've looked at to this point, you can basically assume that they're in the local coordinates. And so, if we were to describe this using an element stiffness matrix, then it would look like the following: so we have F1 x hat, F2 x hat equal to AE over L multiplied by 1 minus 1 minus 1, 1, multiplied by D1 or D1 x hat and D2 x hat. That would be the element stiffness matrix here, with the emphasis on the fact that everything here has a hat, okay, because it's a local system. All right, and so what we're going to do is we're going to basically transform these, okay, into the stationary system, and we're going to use the transformation matrix to do that. Okay. So before we can do that, we have to expand this, right? And so you notice here that not only does everything here have a hat, everything here is in the x direction, okay? But in order to actually apply our transformation matrix, we need to augment this to include the y directions at both node 1 and node 2. the y hat direction. And so I'm basically going to expand this. And so instead of just f1x, f2x, we have f1x hat, f1y hat, f2x hat, and f2y hat. Okay. So we basically expanded here. So we have a vector of size 4 instead of a vector of size 2. And then on the left-hand side, we have, again, A over L. Our element stiffness matrix is now going to be a 4x4 matrix. Okay? And when we expand it to include the y direction, we have to add a lot of zeros into the system. And so that's what our element stiffness matrix looks like now. So you can see that we have our same kind of 1, -1, -1, 1, but we kind of spread them out to kind of only affect the x direction. And then our displacement vector here is now going to be d1x hat, d2 or d1y hat. d2x hat and d2y hat. Okay. All right, so this is probably kind of the biggest jump in logic. So is everyone kind of get why we had to expand this? Because we had to get not only the x directions or the x directions or the x components at each node, but we have to bring the y components in as well, just so that we can apply our transformation matrix. Yeah, I think this part's a little bit confusing. Our question: how did I get 1 and -1? Yeah, good question. So the 1 and -1 come from the original element stiffness matrix up here, right? And so you can kind of see that this part right here goes right here, okay? Because this top left location here, that corresponds to the d1x location. And so let me go ahead and write in. Maybe it will help to kind of write in the columns as well. Okay. And so that 1 there corresponds to the d1x location. This -1 right here corresponds to the d1x, d2x location. This one on the bottom left here is the d1x column, d2x row. And then the bottom right here is d2x, d2x. Yeah. So it's basically just our original element stiffness matrix. It's just everything kind of got spread out and we had to include the y directions. Any other questions on this? Okay. Okay. So let's go ahead and work with this. All right. So we have two vectors here that we need to transform. We have the force vector on the left hand side, and the displacement vector on the right hand side. Okay. So both of these are in the local coordinate systems. So we need to transform these into the stationary coordinates. And so to do that, we're going to use our transformation matrix. All right. And so we actually need to perform, per vector, we need to perform 2 transformations each. So we're going to perform 4 transformations overall. Okay. Let me show you kind of what one of the transformations looks like. Okay. And so let's say that we want to transform the x and y components of the force in the local coordinates on node 1 to the stationary coordinates. Okay. So this is going to be f1x hat, f1y hat is equal to cosine theta, sine theta, minus sine theta cosine theta. F1x, F1y, okay? No hats on those ones, so remember those are the stationary coordinates, okay? And then we have F2, F2x, F2y. Both with a hat is equal to the same transformation matrix, cosine theta, sine theta, minus sine theta, cosine theta, times F2x, F2y. So that's how we would perform that transformation kind of on a node by node basis, okay? Unfortunately, we have to combine these, right? Because the vector that we actually have up here is actually a 4x1 vector, right? So we can't just do two separate 2x2s. So let's kind of combine these into a single system. Okay. And so if we were to do that, it would look like this. We have F1x hat, F1y hat, F2x hat, F2y hat. Here we're going to have a 4x4 matrix. And on the right hand side here we have F1x, F1y, F2x, F2y. Okay. And we need a 4x4 transformation matrix that accomplishes the same thing as our two individual transformations above. Okay. And so this is going to look really weird when you first see it, but I'll explain in a second. And so we're going to have our original 2x2 transformation matrices, but they're all going to be contained in kind of a particular area. Okay. And so for the first transformation for F1 x, F1y, okay, we apply our transformation matrix, and that's going to be in the top left corner of the matrix, but the top right corner is going to be empty. Okay? Because we're not transforming, so we're not interacting any terms between F1 and F2. Okay? And then by that same logic, the bottom left of the matrix here is going to be all zeros. And then at the bottom right of the matrix, we have the same transformation matrix, but we're only applying that to node 2. Okay. All right, and so that 4x4 matrix there is kind of an extrapolation of our original 2x2 transformation matrix, but kind of extrapolated to a 2-node system. Okay. So this right here is kind of the transformation matrix that we will use. Two node systems. Question: what about the AE over L? So we'll come back to that. So we're only working on just one side of the equation, and so we're basically only working on this guy right here. Okay. Eventually, what we're going to do is we're going to take this and plug it in up here, and we're going to do the same thing for the displacement vector as well. So it's going to be a lot of matrix multiplication that we're doing. Yeah, don't worry, I didn't forget that. So the reason we're doing this, remember, is the fact that right now our element stiffness matrix is defined in terms of the local coordinate system, local system, right? We want to be able to define our element stiffness matrix in terms of the stationary coordinate system, so that we can kind of assemble and kind of add different components together for any kind of orientation. All right, any other questions on this so far? Okay. All right, so let's do just that. So let's go ahead and plug this in. Let's go ahead and plug this into the forcing vector in our element stiffness matrix equation. And I'm not going to write it here just because it kind of gets repetitive, but we're going to do the same thing for the displacement side. And just to kind of save myself from writing, let me kind of replace this with a well, actually no. Let me write out the whole thing first, and then we'll go from there. Okay. And so if we do all of that, we get kind of a massive system. Okay. And so to save myself a little bit of writing, okay, I'm going to use the symbol C to represent cosine theta. And I'm going to use the symbol S to represent sine theta. Okay, so just so I'm not writing kind of theta over and over again. And so if we do that, we end up with the following system. So we have C S minus S C 0 0 0 0 0 0 0 0 C S S minus S C. This is multiplied by F1x, Y, F2x, F2y. Okay. Notice the hats are gone, right? So we replace the hats with this multiplication expression here. Okay. This is equal to the element stiffness matrix, which is AU over L at 1, 0, minus 1, 0, 0, 0, 0, 0. Minus 1, 0, 1, 0, 0, 0, 0, 0. Okay. And then we have the displacement vector. So again, we're going to apply the same transformation here to get the local displacements in the stationary system. Okay. So we're going to have another transformation matrix here. So CS 0, 0 minus SC 0, 0, 0, 0, 0, 0. C S S C multiplied by B1x, B1y, B2x, B2. Okay. So these two things here used to be F1x hat, F1y hat, F2x hat, F2y hat, okay, transposed, okay, and then same thing here. So these two group terms used to be B1x hat, B1y hat, B2x hat, B2y hat, transposed, okay. So all I've done is I've replaced the local coordinate stuff with the stationary coordinate stuff with the corresponding transformation matrices multiplied in. Okay. We have a lot of matrix algebra ahead of us. Okay. All right. And so the next step here is to get everything, all the calculations onto the right-hand side. So we need to move this matrix here over to the right. Okay. And so to do that, we need to multiply this matrix by its inverse. Okay. So that's one thing we want to do. So we're going to multiply this entire equation by that matrix inverse to move it to the right. Okay. Luckily for us is that these transformation matrices have a very nice property. The inverse of the matrix, normally to find the inverse of a matrix is kind of a very cumbersome thing to do. But some matrices have this property where the inverse of the matrix is just the same thing as the transpose. And so this matrix is actually one of those. Everyone knows how to take the transpose of the matrix, right? So you just take the matrix and you just kind of rotate it, rotate it just like that. All right. So I'm going to do the rest of this with symbols because I'm tired of writing C's and S's and zeros, although we're still going to be doing that anyway. And so let me call this this transformation matrix. Let me call it T underline. Okay. And so if we move that matrix to the right-hand side, our right-hand side will become this. And so take into account that we're multiplying by T inverse or T transpose. Okay. So on the right hand side, we have T transpose multiplied by K hat. Okay. So this K hat here, that's our element stiffness matrix in the local coordinate system. We haven't done anything to it yet. It's still the same old AE over L and 1 minus 1 minus 1, 1. Okay. And on the right of that, we have another transformation matrix, except this one's not transposed. Okay. And this is multiplied by the displacement vector in the stationary case. Okay. All right. So I've highlighted this part here because so basically we have our old element stiffness matrix. You're pre-multiplying it by a transformation matrix, and then you're post-multiplying it by another transformation. So you're kind of double multiplying by transformation. Okay. And so this quantity right here, this right here is our new element stiffness matrix in the stationary coordinates. And so, of course, actually computing this involves a lot of matrix multiplication with symbols, because I love you, right? But because I love you even more, I'll go ahead and do it for you, just so that we can kind of jump to the result. Okay? And so the result is the following. And so unfortunately, it's a 4x4 matrix. We still have AE over L in front. Okay? And then on the inside of the matrix, we have a product of a lot of triples. So we have cosine squared times cosine times sine times minus cosine squared times minus cosine sine. Okay. Let me write it like this just because it is how I remember it in my head. So the first column is the same as the first row, okay, so I'm just kind of writing it in like that. Sine squared. Minus cosine sine, minus sine squared. In. Cosine squared, cosine sine, sine, and the bottom right we have a sine squared. So this is our new element stiffness matrix for a 2D truss. And you can apply the same thing for a 2D spring as well, except instead of an AE over L in front, you would have the spring constant of the spring instead. Right, so that was a lot of vector algebra, matrix algebra. How did I get the final answer? Yeah, so the final answer I got here was by multiplying these three matrices here. And so these three matrices are up here, right? And so the K matrix is this one right here. So this is the K hat matrix. And then the T matrices are these ones that I've labeled previously as well. So you're going to pre-multiply by the transpose of that matrix. You're going to and then you're going to post-multiply by the same matrix again. And so once you kind of do all that, then that's how you end up with this matrix. So I skipped all those details just because it would probably take us the rest of the class just to do all the matrix algebra. But this is essentially kind of what you get. Any other questions on how we got this result here? Okay. All right. So let's do a very quick example. So let's I know what you're all thinking. Right? I know you're all thinking the same thing. But wow, that derivation was fascinating. I don't care. Let me see how I use this. Right? So let's see how this is used in practice. Okay, so let's write out the element stiffness matrix for a single element. We're going to have a truss bar, and we're going to angle that truss bar 30% relative to the stationary coordinates. So this truss bar is going to be angled 30%. Okay. Let me give you the properties here. Its Young's modulus is 30 times 10 to the 6th psi. Its length is 60 inches. Its area is 2 inch squared. We know its theta in this case is 30 degrees. Okay, and so what we want to do is we want to basically use the expression above to compute its element stiffness matrix, which is now going to be a 4x4 matrix. Okay. And so before we actually start writing stuff down, let's first compute cosine of the angle. And we're going to compute sine of the angle as well. Okay. So cosine of 30 degrees is √3 over 2. Sine of 30 degrees is 1/2. Okay. And remember, these are going to be plugged in as C and S in our element stiffness matrix. Okay. Okay. So let's go ahead and plug all of this in. So we have AE over L in front, so we have 2 inch squared times E 30 times 10 to the 6th psi divided by the length. So the length here is 60 inches. Okay. And then we're going to be multiplying it by a matrix with 16 entries. So, before we embark on this, I know this is going to be very tedious. I know. So, and if you think this is tedious, the homework assignment that I have for you guys, universally, I think I should really quantify this, but just my feeling is that 95% of the students will view me much more negatively after the homework assignment than before. So that's how bad it is. So You know. Well, we have to go through this. We have to go through pain to get to the board, right? And so, you know, and so this, I think this kind of helps you appreciate more about kind of what ANSYS is doing for you, because it's doing all these calculations for you, except to an extreme degree, because those matrices are a lot bigger than this. Okay, so let's go ahead and start computing this. So in the top left corner, we have cosine squared. And so cosine squared is going to be √3/2 squared. Okay. Next to that, we have cosine times sine, and so that's going to be √3/2 times 1/2. Okay. Then next to that, we have a minus cosine squared, and so we have a minus √3/2 squared, and we have a minus cosine sine, so minus √3/2 times sine, which is 1. All right. So that's the first row of matrix. All right. So let me give you guys a little bit of a trick with these element stiffness matrices. So, you know, if you've noticed so far that these element stiffness matrices are all symmetric. Okay. And so what that means is that, you know, if you reflect the matrix across its main diagonal, you're going to get the exact same thing. Okay. And so what I usually like to do when I'm writing these element stiffness matrices by hand is that as soon as I finish a row, I write that exact same row in the column. Okay. And so for instance, we know that the second entry, in the second row, or the second entry in the first row is √3/2 times 1/2. And so by symmetry, this is going to be the same here. So √3/2 times 1/2. Okay. We're going to have the same entry here. So we're just going to bring that one down. And so we have a minus √3/2 squared. And then the last entry in the first row is going to be the last entry in the first column. So minus √3/2 times 1. Okay. So when you're writing these matrices, and you know, it actually can get worse than this too, because there's a section I skip in them, so I don't make it part of the this class anymore. But so we're going to do truss elements. Next, we're going to do beam elements. If we got to frame elements, the frame elements are actually a 6x6 element stiffness matrix, and then you're assembling that together with, you know, 5 other frame elements. So you end up with a global stiffness system that's like, you know, 30 by 30. So you're writing in basically 900 entries there meticulously. I'll just say I got really bad SOQ last semester, so I stopped reading. So now we're stopping at beams. It can get worse, but that's true for a lot of things. A lot of things can get worse. So definitely take advantage of that symmetry, because if you don't, then, you know, you're doing kind of 16 individual calculations. And so if you leverage the symmetry, you're only going to do maybe like 10. Okay. Which is still a lot, but it's less than 6. Okay, second row. So second row we have sine squared. So sine is 1/2 squared. We have a minus cosine sine, so we have a minus √3/2 times 1/2. And then we have minus sine squared, so minus 1/2 squared. Okay. All right, so same thing. I'm going to take advantage of the symmetry, and I'm just going to bring these guys in. So you finish a row, just write that same row into the column. So minus √3/2 half, okay. And minus 1. Okay, and the nice thing is that once you kind of get to the bottom right of the matrix, things start to get a bit quicker. So we have cosine squared here. This is √3/2 squared times cosine sine, so √3/2 times 1/2. And then in the bottom right, we have a sine squared, so that's 1/2 squared. And so of course, you know, you can simplify this, and so you can perform all of that multiplication. And don't forget the AE over L in front too, right? And so that's gonna factor in as well. And then you can kind of complete it from there. Okay. All right, any questions on this example here? All right. So let's actually use this in kind of a bigger problem. So, you know, and so we're not gonna have time to kind of finish everything today. But I at least wanted to start it, just to kind of get you into the mindset of kind of doing this, and then, you know, we'll pick it up again on Tuesday. So this section here is the solution to a flame truss. So I call this another section, but it's really just one gigantic example. So we'll probably be doing it for the majority of class on Tuesday. Okay, but let's look at a situation like this. And so let's say we have a 3-element system. We're gonna have one truss bar that kind of hangs vertically downwards. We'll call this element A. We're gonna have a spring that actually acts at an angle of 45 degrees. So we'll call that spring element B. And then we're gonna have another truss bar that's horizontal in this case, and we'll call that element C. Okay. Let's go ahead and label the nodes, and so we'll label the node in the bottom right, the one where they all kind of meet together, we'll call that node 1. The one that's fixed to the wall up here, we'll call that node 2. The other one that's fixed to the wall for the spring is node 3. And the one that's fixed to the wall on the right, that's going to be node 4. Okay. And this angle right here is 45 degrees. And this one's 45 degrees as well. Okay. So let me give you the properties for this. So for the trusses, and so this is going to apply for both elements A and C. So for both elements A and C, we have a Young's modulus of 30 times 10 to the 6 psi. We have a cross-sectional area of 2-inch square, and we have a length of 10 feet, which is 120 inches. Okay. So element B is a spring, and so for a spring, we're gonna have different properties, and so for a spring, we only have a spring constant. And so a spring constant for that is gonna be K is equal to 250,000 pound per inch. Okay. So that's our problem. So let's take this problem and let's compute. Let's compute the deformations of every single node in this structure using the direct stiffness. So since we're using the direct stiffness method, we're going to be using the exact same process we've used before, except the step for computing the element stiffness matrices is going to be a lot more work involved. It's a 4x4. All right, any questions on just the setup for the problem? Okay. All right, so let's compute just one of the element stiffness matrices and then we'll call it a day. And what you'll see here is that it seems very daunting. Right? So we kind of went through this process here for this example, right? And so it took us a while to kind of just write this one element stiffness matrix, and technically we didn't even complete it because we left all of these as kind of multiplication. What you'll see is that for certain angles, the element stiffness matrix will actually simplify quite a bit. So step one here, write out element stiffness matrices. Okay, so let's do element A first. Okay. And so when you're doing 2D direct stiffness problems, the first question you should ask is that for each element, you should write out the angle. Okay. And so for element A here, we can see that it's a vertical element, right? And so if you rotate from the positive x-axis up to where A is, you can see that the total amount of rotation here is 90 degrees. Okay? And so what we say is that the angle for element A here is 90. And so from that angle, we can compute the cosine and sine of that angle. So cosine of 90 is 0. And sine of 90 is 1. Okay? So this is fantastic here because if you have a 0, okay, right? If you look at the structure of our element stiffness matrix, every entry is the product of either a sine by itself, or a cosine by itself, or cosine and sine. Okay, and so when one of your sine and cosines is 0, that means any term that involves a cosine, we can just automatically just cancel and say 0. All right, and so if we write out the element stiffness matrix for this, okay, and remember, we can't forget that whenever you write out element stiffness matrices, you have to include the node that it's attached to. Okay, and so element A here is attached for nodes 1 and 2. And so we have F1x, F1y, F2x, F2y, okay, equal to. Everything with a cosine is going to be 0. So in fact, everything in the first row has a cosine. So all that's going to be 0. That means everything in the first column is going to be 0 as well. Our second row is going to be 0, 1, 0, minus 1. And so we can write that into the second column as well. Third row is going to be all zeros. And then the last entry in the bottom right is sine squared, and so that's going to be just a 1. All right, and this is multiplied by d1x, d1y, d2x, d2. Oh, forgot. Can't forget AE over L. So remember, AE over L is multiplied out by 5. All right, and so it is these problems are very tedious, but take the shortcuts when you can and try to kind of simplify the process and kind of save yourself from doing just endless amounts of multiplication. All right, any questions on this before we wrap it up for the week? Okay, all right, so that's all we got time for. So on Tuesday, we'll pick up this example again. We'll continue on with elements B and C, and then assemble and apply boundary conditions and all that good stuff. Okay, and so look forward to that. So thank you guys for coming today. I know today was the job fair, so I appreciate you guys coming out. Hope you guys have a good weekend, and I will see you on Tuesday. Okay. Yeah. So I would, so if you did that, it would basically depreciate. The numbers are different, but then it's the same thing. And so what I usually, you've done kind of the first, usually people when they think of it, the first like kind of like a typical. So this kind of a typical. You have the more. And so for your second scenario, I always like think about like what would be like a not so but something that would cause it. Yeah, yeah, my good man. He likes. Yeah, yeah. Yeah, yeah. Oh, it's very nice. Yeah. I thought I responded, yes, that's perfect. It's always good. No, that's perfect. I thought I responded. That's in fact, that's kind of what I did. I thought I responded. Yeah, no. Yeah, so you can have it exactly separate. Kind of like because so I have a I think they haven't gone over this class. Like
That's around 7 of. That's when we were in 45. That's when remember SolidWorks? Was that like 7 to 9 or something? Yeah. I think that's right now. Yeah. So do you go to say hi?
So check.
Dude, he would always go up and ask you like questions because he was in your foods lab. He's like, hey, like, how do I do this? And she's like, it's not the time. It's not the class. Yeah.
I'm certain you could, but I don't.
Yeah. It's a little bit kind of, it's a little bit weird, but once you do it the first time, it becomes.
So I didn't like it. I got some. Yeah. Yeah, I don't think it's gonna be hard. I just not. I well, it was a Sunday.
Hey, you see that?
I opened up one of the ports and I saw it. I don't think it's. I just wanted to open it and go through the process. Yeah. But then I was reading through it. I'm not about to. Like, I didn't even choose it. Yeah. That's why I really learning about it. Yeah. Yeah, like, wait, it was just. Dude, that's what I'm about to do. I'm about to like. That's what I'm trying to do. I like woke up this morning and I was stressing out, thinking about like just supposed to have it. Yeah, that's why I'm gonna.